All right, this is the final hour of Physics 1C for November 5th. And here's the problem. So, we've got current in a wire on the left flowing from A to B, and it's upward and it's increasing steadily at a rate of just di dt. At an instant when the current is I, what are the magnitude and direction of the field B at a distance r to the right of the wire? Feels like it should probably say magnetic field, but I guess we know what B means. It means magnetic field. Part B says, what is the flux d phi b through the narrow shaded strip? C, what is the total flux through the loop? D, what is the induced EMF in the loop? And then finally evaluate the numerical value given some values. This is kind of one of those problems that tries to walk you through how to solve it. And sure, I can do that again, no problem. I will copy this into there. I don't know what I just did. I think I just... Yep, there you go. Okay. So to compare this to the problem on your lab manual, I think the problem you have is really similar to this with one small difference, which might make it kind of challenging, but we'll talk about it, which is I believe that the loop is moving to the right with some velocity v. Does that sound right to y'all? Probably you haven't tried this one yet. That's fine if not. Anyway, eventually you'll get to it, and you can come back and watch this video if you want to review how we do some of this stuff. All right, so we'll go through this one step at a time. All right, part A. At an instant when the current is I, what are the magnitude and direction of the magnetic field at a distance r from the wire? So right here. For that one, we could use Ampere's law if we want to, or we could just say, look, it's a long current carrying wire, and if it has a current I and you're a distance, okay, we're using lowercase I apparently. If you're a distance r away, there's going to be a magnetic field that's produced that looks like this. It's going to have that value right there. And in this case, if the current is flowing up, the magnetic field at this location, what direction would it be? Right here where this blue strip is. If the current in the wire is flowing up this way, what's the direction of the magnetic field in the region where this loop is here? Is it into the page or out of the page? Current flows in a wire here. This is just a loop. We want to know what the direction of the magnetic field created by this wire is. What do y'all think? Out of the page or into the page? Some people saying out of the page. Anyone else have an idea? So the rule is you need to point your thumb like this. And then the fingers of your right hand will be like this. And if you swing your fingers in the direction that they would normally curl, which would be like that, it'll give you the direction of the magnetic field. So I would say the magnetic field in this case is going to be into the page. And it's going to be such that it kind of gets smaller as you get farther away, right? It'll be really small when we get over here because it falls off as... falls off as 1 over r. So that would be the value of the magnetic field that would point into the page, right? All right. Part B says, let's start it right here. Part B says to find the value of the flux, and we're going to use a d phi here. The flux is through just this strip right here, okay? And the way they've drawn this isn't super clear to me, but the thickness of our strip we're going to call dr, right there. And we want to find flux. And what I would say is, okay, well, the magnetic flux then should be equal to something like the size of the magnetic fields, which along that one blue strip there is just going to have a certain value, multiplied by dA, where dA is going to be, well, it's basically going to be the area of this little thing right here. That's going to be our dA. The area of that whole blue strip right there. All right? And we'll say that the direction of that area vector is into the page so that when we do b dot dA, that's just going to end up being b times dA times the cosine of 0. So what we'll get is the dA is just going to be the area of that strip. The area of that strip is going to be L, the length of the strip, times its thickness, which is dr. So dA is going to be L times dr. I'll probably write that down here so it's clear that dA in this case is going to be LdR. And the magnetic fields, well, we've written that right here. So there we go. That's the magnetic flux just through that strip. Part C says, what is the total flux through the loop? Before I move on to that part, does anyone have any questions about part A or part B? Okay, in that case, part C says, what is the total flux through the loop? Well, the flux is going to be equal to the surface integral of b dot dA, which in this case, we kind of already got everything we need here, but we'll go through it again one by one. So the magnetic field we said was mu naught times I over 2 pi r. The dA is LdR. And for our integral then, we're going to have limits. And the limits are going to be from the left edge to the right edge. On the left edge, r is equal to what's defined as a. On the right edge, r is equal to what's defined as b. So we're just going to be integrating from a to b here. Now, it would be a double integral, but I should technically get rid of one of these here. And the reason is because, well, in the, what I guess you might call the y direction or something like this, the magnetic field is constant all along the y direction. So we're only integrating in the r direction. Hope that made sense. The dA, we only have one variable, right? dr. So we only need one integral. All right. I guess I could make that even more clear if I did something else. Just in case, for those of you that are wanting this to look more like what you might have done in your math class. Our dA here, one way we could write it is like this. Okay. So if we wanted to do two integrals, b would be mu naught I over 2 pi r. That doesn't change. If I wanted to do two integrals here, what I could do is I could say this is my r direction and this is my y direction. Okay. In that case, what I would put in here is for dA, I would have some dy and then a dr as well. And then for my y's, I would integrate from like maybe we call this point right here y equal to 0, and we call this point right here y equal to L. So for the y's, I would go from 0 to L, and the r's, I would go from A to B. But then, if you notice, the magnetic fields, this is what I was trying to say a second ago, it doesn't vary as a function of y. All along this blue strip right here, the magnetic field is the same. It has the same value. And so as a result, when we integrate 0 to L dy, you just get L, right? And our integral becomes A to B mu naught I over 2 pi r, and then L from the dy integral times dr. I don't know if that helps or if that was even necessary, if that was just obvious to everyone, but might as well do it just in case. All right. So that's our flux. This is, after all, magnetic flux. I should put a phi b right here. And now we just need to do this integral, right? For which, now, something to keep in mind in this problem is that I is changing in time, but it's not changing in space, right? So I
is a function of time. It is not a function of r, though, right? The magnetic field is a function of r. It's also a function of the current. But I, mu naught, and 2 pi are all constants that can be pulled out of this integral. So we pull those out. We just end up doing the integral from a to b of dr over r. And then that integral is, which one is that one? What do you get when you do that integral? You get r to the 0, because you have to add 1 to the power. You get natural log, that's right. So this is going to end up being mu naught multiplied by I divided by 2 pi, and then multiplied by the natural log of, you're going to get b, well, I'll write it all out. So it's natural log b minus natural log a, but then we write that as log b over a. And there's an L. Yeah, I just dropped the L, as I tend to do in these problems a lot. There's still an L sticking around there. Thanks for noticing that. So that's our flux, which normally the way we'd write this would just be the length times mu naught times the current divided by 2 pi, and then times the natural log of b over a. That is our flux. Okay. Now, I'm reasonably certain in the problem that you have... Oh, God, what's going on? I'm reasonably certain in the problem that you guys have in the lab manual that you should be able to kind of use this as a starting point in a way. All right? You should be able to use that as a starting point. So keep that in mind when you get to it. I mean, you're still going to want to prove everything on the homework itself when you turn it in, but this should be kind of your goal, I believe, is to get to a line like this. All right. Let's finish solving this one, and we're going to come back to this when we're done. Okay, so at the end of this all, we're going to come back to this, and I'm going to talk about what you need to think about for the lab manual problem that you have, because there's just really one change. All right, so that is our flux. Part D says, what is the induced EMF in the loop? How's the grade in the lab manual homework coming along? I have not started yet. Yeah, I apologize. My guess is if you turned it in and you got the answers right, though, you're probably going to get full credit. I really should grade them. It is very difficult for me to grade on a screen, but I will eventually get to it. I really should be posting grades for how you guys are doing by this point in the class, though. But chances are, if you turned it in, you're probably going to get full credit unless you just made a lot of mistakes, in which case you might get 8 or 9 out of 10. I usually don't take more than like 1 or 2 points off per problem, and that's actually usually because people just do really well on this stuff. So yeah, so as long as you put the time in, you got the right answer and stuff like that. I'm just going to check to make sure that there was, no mathematical errors or anything like that. Okay. Not much to worry about, though. I'm not, I know how hard those problems are. And I'm generally very impressed with the work that people put in to get them right. All right. Part D. What is the induced EMF in the loop? Well, if we know the flux, this is really easy at this point, because the induced EMF in the loop, that's this loop right here, is just equal to negative n, which n is going to be 1 again, and then times the time rate of change of the flux. So in this case, the only thing that's going to be changing in time here, B and A, just to go back to the picture again, A is the distance from the left edge, and B is the distance to the right edge, so those are fixed quantities. Mu naught is fixed, pi to L. So it's really just I. So when I take the derivative of that whole thing right there, what I'm going to get is L mu naught natural log of B over A divided by 2 pi, and then times di dt. And then in part E, what they want us to do is just plug numbers into this, and those numbers are given right there. If I go down a little bit, I can't see it still, but if I go back up just a little bit, we can plug everything in. So plugging in the values that they give us then, the induced EMF should be equal to, L is 0.24, U naught is 4 pi times 10 to the negative 7, natural log of B over A, 36 over 12. We don't really need to use units here or anything because it's a ratio, so the units will automatically cancel out. We divide by 2 pi,
and then we multiply by di dt, which is positive 9.6 amps per second. And that's a decimal, and that's a multiplication sign.
And if we multiply all those out,
did I miss any? Did I miss anything? I probably did. Let me know if you see anything missing.
I got 5 times 10 to the negative 7. You always get really tiny numbers whenever n is 1. All right, so E is equal to, there's a negative sign. We'll just do absolute value. I got 5.1 times 10 to the negative 7 volts. Do you all agree? All right, good. Okay, any questions at all? I said I'd come back and we talk about this piece right here. Now, the homework problem that you have, I want to say the only difference, but I can't remember it. I have to pull it. I have it here, but it's kind of dark in my house. I can't read it. Okay, so the only difference is that the loop is moving to the right. And I believe that the current is not changing in the wire. I could be wrong about that part, though. I can't remember. But I know that the loop is actually moving away. All right? It's moving away. So, up to this point, the calculation you're going to do is going to be the same. The derivation you're going to do is going to be the same. The difference is going to be that A is going to be a variable. The loop is moving to the right, right? So A is going to be a variable, represented by like X, for example. And then B is technically going to be a variable too, where it'll just be X plus the length of the wire right here. So these two quantities inside of here are going to be variables, basically. A is going to be represented by something like X, and B is going to be related to something like X plus a constant, okay? Inside of your log right here. And then, because it's moving to the right at a constant speed, you're going to know that dx dt is the velocity, and that's going to show up in your answer. So basically what you have to do in that problem is when you do this operation to calculate the induced EMF, and you're taking your derivative, you're going to be taking the derivative of basically this term right here, the log term, because both of the quantities in here are going to be varying with time. And I think everything else in the problem is going to be constant. Although it's possible the current is also changing. That would make it a little bit more challenging. But I believe it is just the things that are inside the logarithm here that you're actually going to have to deal with. So you end up taking the derivative of your logarithm and, you know, doing some chain rule stuff, and then yeah. So that's something to keep in mind. Do I want to say anything else about that? There's some really common pitfalls that I always saw when I was grading this problem. Just remember, when you're taking the derivative of something like this, when the variables inside of the thing are also derivatives with respect to time, you need to use the chain rule. You know, you take the derivative of the outside, you multiply by the derivative of the inside, and the derivative of the inside is going to be a quotient, right? So when you're taking the derivative of the inside, you're going to need to use the quotient rule, and then after using the quotient rule, you're again going to have to multiply by the derivative of the inside. Does that make sense? There's like a double chain rule thing that's happening here. So don't forget your 190 skills, I guess. It's all math 190 stuff. It's all just derivatives. But my memory is that it's a very complicated derivative, and people usually kind of miss some things about it. Okay? So you're not taking ddx. Your thing is going to look something like natural log of, I think it's going to be like x plus a constant divided by x. And what I'm trying to say is that since you're doing ddt of this, it's not ddx, right? You're taking the time derivative. You need to take the derivative, and then after taking the derivative, you're going to have to multiply by the derivative of the inside. So you have to take the derivative of the outside and this quotient thing, and at the end you're going to have to multiply by this. Okay. All of that stuff hopefully will make more sense when you actually do the problem. So remember what night this was. It's like November 5th, and go back to this description for when you do that problem, in case you need some help. Okay? Any questions? It's amazing. Oh, no, it still looks bad. I was going to say, when I link this into the Discord, the little artifacts that show up, like, in here and stuff, they kind of disappear whenever I linked it, but I think it's just because it's smaller. And okay, let us spend the last 20 minutes or so we have in class talking about inductors then. Well, really, inductance, inductors. That's what we want to talk about. Really, we're talking about inductance. Okay. So let's consider a really simple circuit. So let us say that we have a circuit, and this circuit is going to have a battery, a resistor, and a switch. And the idea here will be that we close the switch at t equal to 0, as we often do. Okay, so this is a topic that came up at least once before, but what we're going to be talking about here is back EMF. So if we close the switch at time equal to 0, we know that there's going to be current that starts to flow in this direction. Here, let me go back to having a thicker version of this pen. We know that there's going to be a current that's flowing in this direction here. Now, the fact that we've turned the current on means that the current is going to build up from 0 up to some maximum value over time, right? So the current, let's just say it doesn't instantly reach that current level I. And even if it did, the current in the wire is increasing. It increases from I equal to 0 up to I equal to E over R over some time. But the thing to think about as a result of that is that this is going to create induction. It's going to create induction according to Faraday's law and Lenz's law. Because if the current in the wire is increasing, what does that mean about the magnetic flux through the loop itself? You have a changing magnetic flux. That's right. Is it increasing or decreasing? That's right. It's increasing. So magnetic flux through the loop is increasing. As a result of that, there's going to be an induced EMF. And the direction of that induced EMF, is it going to be in the same direction as the current or the opposite direction as the current? Opposite, yeah.
So we'll draw that on our picture in green here and say that there's going to be an induced EMF, or put more simply, an induced current that is opposite to this. So we'll call this I induced. And that I induced, this is sometimes referred to as back EMF because it's opposite the direction of the applied current, or it's referred to as self-induced EMF. Because after all, it's EMF that was induced into the wire
due to current in the same wire, right? I mean, if we just go back to the previous problems that we've been doing here, we're always talking about two objects, right? You've got the object that has the current and the object that gets the current induced in it, right? But when you have a loop of wire, you're going to have an induced EMF that opposes your attempt to basically turn the current on, you know? Okay, do you guys all follow those steps of that process there then? It's all about Faraday's law. That's what inductance is all about. Inductance is a type of measurement of how much induced EMF you're going to get. Okay, that's what inductance is. So the word inductance, what it means is it's a measure of how large the self-induced EMF is going to be. And the truth of the matter is, the effect of all of this, the big picture effect of all of this, is that in any type of a circuit that has a closed loop, it's impossible to have the current instantly jump from 0 up to some maximum value. Like, this always has to happen over some time. And the time that it takes is going to depend on the inductance of the circuit. And I'll put it in an even simpler way. The time that it takes is going to depend on how many coils you have in your circuit. Okay? So if you have a circuit that happens to have within it like a solenoid is an object that just has, a whole bunch of coils in it, right? Imagine that you design a circuit and you just intentionally fill it with a whole bunch of coils of wire like this, right? Well, that's going to cause an even bigger self-induced back EMF. Because one of the things that shows up in Faraday's law is that N that shows up in front, right? The number of turns. So the more coils you have in your wire, the larger that this effect is going to be. And the effect is going to be that a circuit that has a lot of coils is going to have current changes that are going to tend to be kind of gradual as opposed to instant. That's right. So Ash says, apparently the inductor could help smooth out the inconsistencies in alternating current because of this. That's right. That's right. It can help smooth out things, right? So the effect is that current in a wire will build up gradually instead of instantaneously. And it works both ways, actually. It works both ways. Current in the wire will build up gradually instead of instantly. Okay? Let me show this little picture that I took from the book because it might be helpful to people. All right, we already did this one. So this is your book's picture of it. So you've got a circuit. Let's look at the picture here. There's a circuit, positive, negative. Current wants to flow this way. Now in this circuit, there's intentionally this big coil here. This is what we would call an inductor. The word inductor literally just means coil, by the way. Okay, I'm just going to say that. The word inductor is a device that's really good at inducting, which is, a coil. They mean these are synonymous words, okay? Coil of wire, solenoid, all these things are inductors. Yeah, the idea is that the current flowing here produces a magnetic field. And in a way, as the current's flowing, it has to kind of build that magnetic field up. And it doesn't happen instantly. It starts off and it's kind of gradually building up current. And then, once the current's established, you've got a magnetic field. The really cool thing, too, is that when you try to cut the current off, that magnetic field contains energy in it, and it doesn't just instantly disappear. So the magnetic field can kind of actually become a source for a current flowing in the opposite direction as it tries to decay. All right, I'm going to show you, I think first thing we'll do is we're going to build a circuit. Wait, is it right here? Oh, there it is. We're going to build a circuit that has inductors in it. I did one before class, but we're going to build it completely from scratch here. And I'm just going to show you what these things do, okay? Do I have to do the... It can accumulate voltage, Ash, that's right. It slowly decays in current as the power source is removed. I just realized, do I need to... do I have to do the math first? Do I have to do the math stuff first before I show this to you? I feel like this is something that as soon as you see it, it will make so much sense to you. Well, I'm just going to say this, okay? We use the symbol L for inductance, okay? And the value of L, okay, is equal to N times phi B divided by the current that flows through your inductor, okay? This is what we call inductance. All right. And it's something that kind of depends, it depends mostly on, again, like how many coils you have. All right? Depends on how many coils you have. So let me give you an example. So what's contained in this? It's L, it's flux, it's number of turns. Okay. And an example of what this would be a solenoid. Okay? A solenoid is just basically a bunch of coils, right? And a solenoid has a magnetic field that's given by mu naught multiplied by little n, which is the number of turns per unit length, and then multiplied by the current that flows through it at any moment in time. Okay. Another way to write the magnetic field of a solenoid is mu naught times n divided by L times I. And what do these things represent? Well, the idea is that a solenoid is basically you've got a long core and you wrap wires around it. These wires go around and behind like this. It has a length that we call L. It has a number of turns that we call N. This one has 1, 2, 3, 4, 5, 6, 7, 8 turns per unit length there. And then we have the end cap here, which is A. Now, to find the inductance of a solenoid, all we have to do is to do the following. The inductance, L, is going to be equal to N, which is number of turns in the solenoid, the same N that's here, multiplied by the flux. The flux is going to be B, which is mu naught times N times I, and then you need to multiply by the area, A, and then you divide by I. The currents will always cancel out when you do stuff like this, and this gives you the inductance of a solenoid, and it would be equal to mu naught. Little n we said was N over L, so this is going to end up being mu naught. You get N times N, which will be N times N, so N squared, and then times A divided by L. That is the inductance of a solenoid. Okay? That is the inductance of a solenoid. Notice that it only depends on geometry, right? It only depends on the physical aspects of the solenoid itself, and the biggest thing it depends on is the number of turns, okay? We know that mu naught is a very tiny number, right? Area could be just whatever the area. The end cap is, length is how long it is. It's the number of turns that matter. So with solenoids that are designed to have a really high inductance, what you're going to see is just a whole bunch of coils. Just a ton of coils. The N is the biggest part of it here, okay? Now, what do the units of this look like? Let's look at the units. Mu naught has units of Tesla meter divided by amp. N has no units at all. You said if there's not a vacuum between it, wouldn't this independence not be true? You mean like the inside of it being a vacuum? The inside doesn't have to be a vacuum. If it's a vacuum, you get this quantity here that's mu naught. If it's not a vacuum, if it's like iron, you use something called mu, which doesn't have a little naught right here, and it's just a bigger value. In fact, when you put iron inside of it, it makes the solenoid have an even bigger inductance by a factor of like maybe even 10,000 or something like that. So just putting an iron core inside of here makes the inductance even bigger, actually. Okay. All right. So units, we've got mu naught, which is Tesla meter divided by amp. We've got N, which is number of turns. That does not have a unit. We have A, which is meters squared, right? And then we have L in the denominator, which is meters. So actually what ends up happening here is these two meters cancel, and our units are basically Tesla meters divided by amps. And if we want to know what that is in some other type of a unit, so we want to do something with our Tesla meters here. A choke. Yeah, sometimes, inductors are related to chokes. What's a good way to rewrite this one here? This is called the Henry. Yeah, that's actually right. That's the name of the unit. How do we get to the Henry, though? Because the Henry is something like volts per amp second, I believe, or something like that. And so how could we see that? Well, I know Tesla meters squared over seconds is a volt. So if I move some things around here, then a Tesla times a meter would be a volt divided by a meter times a second, right? Do that right? Yeah, divide one of the meters, multiply the second over here. So this could become volt seconds over amps times, there's a meter in the numerator and a meter in the denominator. That was really confusing how I did that, but we got volt seconds per meter is the Tesla. And yeah, so these cancel. So you end up getting that the unit, that we call this a Henry. So 1 Henry, I believe Henry figured out Faraday's law at the same time as Faraday, if I remember correctly. And my memory is that he did the mathematical version, the kind that we're more familiar with. So this 1 Henry is equal to a volt second per amp. So it's like volts divided by amps per seconds, basically. Volt second per amp. And there's one other thing we can say about these, which is that the EMF associated with an inductor, which we'll call E sub L, right? Now, why do I care about this? Well, let's write some other thing. For a resistor, we had the resistor EMF was what? I times R, right? For a capacitor, we had the capacitor EMF was, I think, Q over C, right? The EMF associated with an inductor is negative L times di dt. What do these things do? A resistor has the effect of basically slowing down the current, right? Because E over R is equal to I, so the bigger that R is, the smaller the value of the current is, right? Right? For this, what we could say is if I take E over L, this is equal to negative di dt. So an inductor has the effect of altering the rate of change of the current. The rate of change of the current is going to be dependent on the size of the inductor. The larger that the inductor is, the more kind of smooth the rates of change need to be here, right? If the inductor is tiny, the rate of change of the current can be high. What does that look like? Well, that would be something that like oscillated up and down really quickly in terms of current, right? This would be L small. And if I have a device that has a large L, it's going to have much smoother kind of changes with tiny derivatives, right? Okay, a resistor slows down current. An inductor slows down the rate of change of current within a system. Does that make sense? It makes the current kind of sluggish, so that it can't change instantly. All right. Does that all make sense? All right. Let's look at what it looks like with light bulbs, because I think that makes it a lot clearer. We'll do a mechanics analogy here in a second that I hope will help to drive this home for you. But before we do that, let's actually look at this system here. All right. Reset all. Yes. Can you use an inductor to prevent a short circuit? Maybe. All right, we're going to have a battery, and we're going to use a wire to connect it up to basically, we'll do one at a time. So what we'll do is we'll put one light bulb in here, and then we'll throw an inductor in here. Now we can look at the value. This inductor has 50 henries. That is utterly massive. 50 henries is a gigantic inductor. So that's going to have a huge effect on the attempt to change the things in this current. So there we go. We've got a light bulb so we can visually see what's happening with the current in terms of the power output of the light bulb. We've got a battery, and we've got an inductor right here. Notice that the inductor is literally just a bunch of copper wire that's been wrapped around. I mean, it's amazing. It's literally just a big coil. That's all that it is. Okay. And we want to connect all these together here so we make a nice simple little circuit. All right, so what I said was that the inductor has the effect of slowing down the rate at which the current builds up. You know what I want to do actually first? Let's look at what happens when I don't have an inductor in my system, okay? We close this. Something's not connected. Did I just not close it? Nothing's happening. These all look connected, don't they? Play? Boom. There we go. Well, that kind of ruined it. All right. So if I close the switch, the light bulb comes on. Right? Pretty simple, right? Let's do this. Let's make this a lot more powerful. So now I close the switch and the light bulb gets really bright and everything moves really fast, right? There we go. Open the switch, there's no path for the current to flow, so the current instantly stops, right? All right. If I put an inductor in here, you'll see instantly a difference. All right, so now what happens is if I close the switch, the current is going to build up slowly. Like that. See how it wasn't instantaneous? It took some time. Whereas again, just to kind of, here, let's make it have less inductance. If it has less inductance, Tybee, you're picking up everything with your mic. You need to mute your mic. So if I make it have less inductance, so it has 10 henries now, that means that it's going to have less of a resistance to changes in current. So it gets brighter faster. If I increase the inductance so that it's like 100, so double the value it had at the beginning.
You do.
Ty, I'm just gonna mute you. This is stupid. I shouldn't say stuff like that, but I don't really have time to do that. All right, so 100 henries, right? You double the value, and now it takes much longer for it to actually light up. So that's what an inductor does, is it slows down the rate at which the current can build up. Now, once the current's already flowing, it doesn't really do much at this point, right? We can do that, Ash, except right now, it can't power the light. Why can't it power the light right now when I open it up? No circuit, right? So what do I need to do to allow that to happen? I need to basically complete a circuit on the top, right? So let's do that. So let's throw in here, let's open this. Let's give it a path so that the inductor can do exactly as you're saying there, Ash. So yeah, I knew that was gonna happen. We need to add a resistor into the top here, so that it doesn't like burn the circuit up. Okay. this animation is kind of funny that it does that part. All right, so now here we go. Oh, it still doesn't like it. Okay, let's do, well, there it's doing it. Discharge the inductor. Let's reset dynamics, and let's see if we can get this to work better now. What is he getting mad about now? There's resistance at every point in the circuit. Maybe not out here. Is it still gonna do it? Yeah. Okay. Now let's give it a resistor down here too, so that it doesn't yell at us. Should be fine now, I hope. All right, reset dynamics. Yeah, fire. That's what you get when you have resistance, right? All right, here we go. All right, slowly building up. Now there's even more going on here, which is that because you have resistors here now, it's going to take even longer to build up. But there it is. Now let's see if what Ash says is true. What Ash is saying is, can I take out the battery after the circuit in the inductor? Will it power the light for a bit? Let's see. There it goes. As the magnetic field inside of the inductor decays, it basically can power the light bulb at that point. And you may have noticed something about the direction. See, the fact that these things are here, this is bothering me. So we're going to need to do something here to fix this. Because we can do this with another set that also has the same kind of setup here. So let's put another inductor up here. And let's connect that up. Like that there. I don't think I need this anymore. I'm pretty sure this is the one I connected earlier, and it worked just fine. All right, let's reset dynamics. Let's show values here. And let's use two different inductors now. They're not technically instantaneous, Astrolover. It's so fast that you can't discern how quickly it turns on. But it tells you that they don't have 100 henries in them. This, it turns out, I think a lot of the problems you'll do, you're going to have millihenries and stuff like that in them. And so if we were at the school, I think the biggest inductor we have at the school is 0.3 henries. The ones that you guys would do labs on. So microhenries, millihenries. Okay, so look at this. Now we've got two light bulbs. We've got one switch. We have a 50 Henry and a 100 Henry, right? Which one is going to light up the fastest? Remember that what an inductor does is it slows down the rate at which the current can build up, right? The bigger it is, the more it's going to slow down. So which one of these light bulbs will reach its max brightness first? Will it be the one connected to the 50 Henry one or the one connected to the 100 Henry one? Yeah, top one, right? Let's watch. There it goes. Already fully bright. The other one's still just now getting there. All right, now, of course, it's burning too, but whatever. If we open this, see, now this is where it, like, crashes. Okay, so I've done something slightly different here, and I don't know what it is. I don't know what it is that I did, because, like, when I did this right before class, I didn't have to put the resistors in here. Let's put a resistor in. Let's change the resistance to, like, not 0, but, like, 0.1 or something, because I don't want this to alter what's happening in the system. Let's try this one more time. Okay, there they go. They brighten up. And then we turn them off. Oh, it doesn't like this at all. Why doesn't it like it? They are trying to move. I don't understand why it's doing this. Okay, there's that, and then when I open it, it just is like, it flips out. I know I've done this demo before, because what should happen is the circuit that has the larger inductor should kind of win out, and the current should flow like that. Let me... Oh my god, what is going on here? All right, reset dynamics. Let's put an inductor back in here, and discharge. Let's make both of them the same, or one like just slightly different. That one's 50 and that one's that. Okay, what happens when we do this? And then when we do this. Okay, it's not getting mad at me as much anymore. I think that the fact that one was 100, maybe it was the reason why I was doing it, although I'm quite certain that I've done this before where it wasn't like this. Okay, let's make one of them like 35. Show the value. Okay, so now let's reset dynamics again. So now let's do this again. So they charge up. This time the one on the bottom charges up faster, and then so it's the fact that it's starting to burn up that's the problem. Do I need to make this thing have... Oops. Let's give it more ohms. Maybe that'll make it happy. Reset dynamics. I just want to show you guys the way that this ends up working out. It's kind of like a collision. Okay, they both brighten up. Current's all flowing just fine. And now if I open it, it does work in the classroom. It's true. It's not. Well, I'll work on this, and I'll come up with something next time that'll be a little more useful. But hopefully you get the idea. One final thing I want to say about inductors, because we're out of time right here, is if we want to think about Physics 1A and what an inductor is like, okay? What is it that gives the inductor more henries? Great question. This is how you find inductance right here, okay? This right here. So mu naught is just that's something that you can alter by putting like an iron core inside of here. N is the biggest thing, though. It's the number of turns, right? So if you have 100 turns versus 200 turns, 300 turns, you're going to get more inductance, basically, right? And the idea is because when there's more turns, right, that's more induction that can occur, right? I want to kind of take this back to Physics 1A, though, because for me, personally, that always makes understanding these things a little simpler. So EMF, we use the word EMF, which means electromotive force, which means that when we write anything down with an EMF, in Physics 1A, you can think about that as having kind of an analogous quantity, which would be force, okay? And current is basically kind of like velocity, which if you do the derivative of current, then, which is the derivative of velocity, what would that be? What's dv dt give you? Acceleration, right? Okay, you want to guess what the L represents then? Mass, that's right. Moment of inertia is a perfectly good example, but then you'd just be doing torque equal to I alpha. Either way you want to think about it, I think mass is the easiest thing to think about. This is your F equal ma for electricity and magnetism. So inductance is similar to mass, right? Inductance is similar to mass, and it's similar to mass in the following sense. Say you take a cart. The demo I do in the classroom is just you take a cart. It's got a bunch of stuff sitting on top of it. It's very heavy, right? You walk up to this cart and you try to push it, right? If I want to take a cart and I want to take its velocity and take it from 0 up to 10 meters per second, I can't do that instantly, right? I can't. It's just not possible. It takes time to accelerate anything that's massive. That's what Newton's second law tells us. So yeah, what you said, Ash, is very good. Mass resists change in velocity, just like inductance resists changes in current, right? So an inductance is a measurement of sluggishness to changes in current, which you can think of as being similar to anytime you try to move an object. Like if you try to take a car that's in neutral and you try to move it, even though it has wheels and those wheels are going to have low amounts of friction, you can't just take that car and instantly get it up to a speed. In addition, once the car's already going a certain speed, it takes something to stop it. It has inertia, right? And that's what an inductor does. So it's like the inductor, it resists your attempt to get the current going, but once it's going, it doesn't want you to let the current stop. So when you try to turn the current off, it'll keep going for a little bit, basically. All right. So we went a little long today, but I think that's okay. It's some complicated topics. And we'll learn more about inductance, and we're going to look next time at what happens when you put an inductor and a resistor together. What happens when you put an inductor and a capacitor together? That one's really interesting. You start getting some oscillations, and then we'll put together an inductor, a resistor, and a capacitor, and we'll talk about radios. So that's basically what that is. All right. So yeah, resistance to change. Exactly. Mass is a resistance to change in velocities, and inductance is a resistance to change in currents. So that's all it is. Yeah. So I like that analogy too. I'm glad you do as well. All right, I'm going to stop right there. I will stick around for questions.